Hello and welcome to NHP's public webinar series. The topic for today's discussion is surge protection. The key areas covered by today's session will include what are surges and where do they come from, the different technologies available, key standards and what the symbols mean to each, and how to select a surge diverter to ensure adequate protection to your facility. To begin the discussion on surge protection, it helps to identify what a surge is and where they come from. We must firstly understand the requirement for surge protection and what events occur that require the installation of a surge protective device, or SPD. This brings us to transients, or otherwise known as surges. Transients are short-term overvoltage events, which can reach tens of kilovolts. However, they only last for a very short duration. This is in the realms of microseconds, up to a few milliseconds. It's the duration of time which sets a transient apart from another phenomenon called temporary overvoltage. This differentiation is very important as a surge diverter is not designed nor intended to protect against temporary overvoltage. This can be described as a rise in voltage over multiple cycles of the 50 Hz waveform. So some of the common faults caused by transients or surges include premature aging of electronic components, component malfunction, data corruption or loss, equipment failure, or disruptions to service. Transients can occur from many different sources, whether they be from atmospheric events or internally derived. One of the main contributors we must consider is lightning. Lightning is not the most common, but it has the most destructive power, and therefore, if a surge diverter is sized to protect against the effects of lightning, the installation should be protected from all other sources of transients. The damaging effects of lightning can come from a direct strike, or they can come indirectly when lightning hits nearby overhead cables, for example. Damaging transients can also be induced on the supply cables because of inductive coupling. But basically, any metallic cable entry or even metallic pipework is capable of transmitting surge energy into a building. Looking at lightning generated transients a little closer, these charts are known as chronic or isochronic maps, and they represent the number of thunder days per square kilometre. This provides a historical representation of how many lightning strikes occur per square kilometre per year and can be used as guidance on how likely your facility is to receive a transient as a result of lightning. The darker the coloration, the higher the lightning risk. Conduced overvoltage involves a direct lightning strike via a lightning rod or other nearby object such as a lighting tower, mast or antenna. In high-risk areas of lightning strikes, it is preferred to control when the strike occurs. This is the primary job of a lightning rod. The energy then travels down the lightning rod, down the down conductor, to Earth, causing a rise in the ground potential in the local vicinity. This creates a differential between the local ground and the system ground, which causes current to flow through the earthing system. This will potentially damage any equipment referenced to Earth. Induced overvoltage can also occur when lightning strikes nearby power cables. Transient propagates along the power line into the facility, once again potentially damaging any equipment referenced to Earth. Induced overvoltage is where lightning strikes a nearby object, which causes a large electromagnetic pulse of energy. This energy is induced onto the nearby power lines and can then propagate into a facility's electrical system, potentially damaging equipment. Induced overvoltages are typically lower in energy than conduced overvoltages. Other common sources of overvoltage transients are utility grid switching, switching capacitor banks, or switching largely inductive loads. The typical profile of a transient caused by external influences, such as lightning, are an impulse. The impulse has a sharp wave front with a tapered trailing edge. These impulses are generally less frequent, however they contain more energy as they are longer in duration. Peak voltage can rise to as much as 20 kV or sometimes even greater. Internal transients are typically in the form of a ring wave that consists of a large peak that has several trailing peaks, which generally lower in amplitude. In inductive loads, there is magnetic energy stored within the coil while energized. Upon de-energization, this stored energy continues to flow, which causes a high voltage pulse. This pulse then creates an arc across the switch or contactor's contacts while they are beginning to open. As the gap between the contacts increases, the arc is quenched. The voltage rises again and a restrike is formed. This is what causes the multiple trailing transients. Internal transients are smaller in nature or in energy, however, they are much more frequent than impulse type of events. Now we understand where transients originate from and how they can enter a facility. Let's look at the different technologies used to protect electrical equipment from the damaging transient energy. The purpose of a surge protective device is to protect critical and sensitive electrical equipment by diverting and limiting transient voltages and currents. The SPD, which is normally connected in parallel, acts like a switch which changes state based on its voltage. In normal conditions, the SPD has a high impedance and appears as an open circuit. However, when a high voltage transient occurs, the SPD becomes a low impedance, becomes conductive, and offers a path of lower resistance, shunting the energy to ground. Note that it doesn't shunt all transient energy to ground, and that a residual voltage remains. The equipment being protected will still be subjected to this residual voltage. There are two possible scenarios that follow. If the residual voltage remains lower than the insulation capacity of the equipment, then in theory no arc forms and therefore the equipment should be protected. If the residual voltage increases above the insulation rating of the equipment, then it's likely that an arc occurs within the equipment and the equipment is damaged even if a surge diverter is installed in circuit. This condition may occur with an improperly selected surge diverter, or where the surge contains more energy than anticipated. There are two main types of surge diverter technologies. There are voltage limiting components and voltage switching components. Voltage limiting technologies such as varistors and diodes effectively clamp the voltage to a safe level while conducting the surge energy to ground. Voltage switching components, also known as crowbar devices, switch to a low voltage state when the detected transient voltage exceeds a particular threshold. This low voltage state reduces the voltage seen by the equipment. Looking at varistors in a little more detail, the resistance of a varistor or variable resistor, and most commonly a MOV, drops significantly when the voltage exceeds a limit. This then clamps the voltage near to the limit. As can be seen from the chart, a MOV is able to reduce the let-through voltage down from V surge to V clamp. The level of V clamp is the approximate voltage that the equipment being protected will be subjected to. The MOV is widely used in SPD construction and offers a good balance between surge rating and clamping voltage. MOVs have a very fast reaction time and leave a low residual voltage, which makes them ideal for protection of electrical equipment attached to the AC mains. The downside, however, is that a MOV degrades with every single discharge. The amount of degradation depends on the amount of energy it is conducted. One large transient may be enough to achieve end of life, or it may take hundreds of small transients to eventually break it down. Now to diodes, or transient voltage suppressor diodes. They are ideal for protecting semiconductor components from high voltage transients. They can respond to overvoltage events faster than any other type of surge protection. Transient voltage suppression diodes can fit a wide range of circuit protection applications, but were primarily designed to protect I/O interfaces in telecommunications and industrial equipment, as well as computers and consumer electronics. Now on to the voltage limiting technologies. Spark gaps and discharge tubes. A spark gap consists of two electrodes which are separated by a gas, normally air. When enough voltage is applied, the air is ionized and a spark forms between the electrodes. This creates a short circuit and allows current to flow. It is now in what is called its activated state. Once activated, the normal system voltage is enough to maintain the crowbar device in its low voltage state. It remains in this state until the voltage decreases below the extinguishing value or an upstream protection device trips. Gas discharge tubes operate similarly. However, the medium is an inert gas. At normal voltage levels, the gas is a poor conductor. However, when the voltage increases from a transient, the gas is ionized and the gas discharge tube becomes a good conductor. Spark gaps have a high discharge capacity, which makes them suitable for discharging large currents, such as those received from lightning. Once activated, the residual voltage is very low. However, to activate them in the first place, they require a large peak, which results in a high initial residual voltage until fully activated. The benefit of this technology is it doesn't degrade anywhere in the same way as MOVs do. So to compare the technologies, spark gaps have a high surge current withstand and don't degrade. However, they have a slow response time and still let through a high initial peak. MOVs have a high surge current withstand and a fast response time. However, they degrade with each transient. And the diodes have a very fast response time and don't degrade. However, they have a much lower surge current withstand. There are three main standards which are applicable in Australia and New Zealand. These are the UL 1449, Standard for Safety Surge Protective Devices. This standard is mainly developed and adopted by North America. Then there's the IEC 61643, Low Voltage Surge Protective Devices standard. This is the standard adopted by Europe. These two standards are product test standards and are utilised by the surge diverter manufacturers to design, test and rate their products. The third standard, which is better described as an application guide, is the AS-NZS 1768 Lightning Protection Standard. AS-NZS 1768 is not a product test standard and therefore no surge diverter can be built or tested AS-NZS 1768. But having three standards puts us in a unique situation, as most countries are aligned to either UL 1449 or IEC 61643, but not both. This allows us to use product design for either the American or European markets. However, this causes issues. These standards sometimes have the same symbols, however, each standard has its own tests behind those symbols, which can vary between the standards. The next few slides will aim to explain what the symbols mean and how they differ between the standards. The typical parameters of an SPD include UP or VPR, otherwise known as the voltage protection level or voltage protection rating, and it's a parameter that characterises the performance of the SPD in limiting its voltage across its terminals. Then there's the I impulse or impulse current. This is the impulse test current on the 10350 waveform, which describes a measure of the ability of the surge diverter to conduct an extreme magnitude of current. Then there's the I max or maximum surge current, which is a measure of the ability of a surge diverter to conduct a large amount of current using the 820 microsecond test current waveform. Then there's the nominal current, IN. This rating describes the longevity of a surge diverter and its ability to withstand multiple impulses on the 820 microsecond test current waveform. And finally, there's the UC or MCOV, which is the maximum continuous operating voltage. Looking at the nominal current a little closer, this rating describes how well the SPD deals with multiple transients and can be used to describe the longevity of the surge diverter. Tested using the 820 microsecond waveform, this simulates the SPD's ability to protect against induced or switching transients. The nominal current is also related to UP. The maximum surge current represents the ability of the SPD to divert large transient currents. This rating uses the 820 microsecond test waveform. However, the three standards differ in their interpretation. The AS-NZS define this as a one-shot rating, however there is no test behind it. The IEC standard defines 5 incremental impulses, however only one is at the full rating of I max. And the UL standard does not define I max and instead allows for the sum of all the parallel connected protection devices. One key note from the IEC standard states that if the residual voltage achieved at I max is higher than the voltage protection level, and especially if it is higher than the impulse withstand voltage of the equipment to be protected, then there is a risk that the SPD will survive such a stress, but the equipment will not be protected. So in simple terms, a device with a higher I max does not always mean better protection. Impulse current represents the ability for a surge diverter to discharge an extreme amount of current that would normally be associated with an impulse type of event, such as lightning. As mentioned previously, impulse transients carry more energy, and therefore some SPDs are subjected to additional tests to receive a Type 1 or Class 1 classification. These tests are conducted on the 10350 microsecond waveform, and product labelling helps to identify these SPDs as suitable for installation at the service entrance. However, it is only the IEC standard that actually recognises I impulse. The AS-NZS standard does state that a factor of 10 may loosely be used to compare the I-impulse rating with the I-max rating. For example, an SPD withstanding a 100 Ka 820 microsecond impulse might be expected to withstand a 10 Ka impulse on the 10350 waveform. I-impulse does not exist and is not recognized by the UL standard. Comparing the 820 microsecond to the 10350 microsecond waveform, the orange shaded area represents the energy contained in the 820 microsecond test wave, and the yellow area represents the energy contained within a 10350 test wave. The peak voltage in this case is the same, however, the difference is the time period in which the transients are sustained for. As shown, there is far greater energy imparted on the SPD in the I-impulse or 10350 test. Voltage protection level is perhaps the most critical parameter of a surge diverter. It defines the residual voltage across its terminals. This voltage is also seen by the equipment being protected, and therefore this parameter is the one which defines whether a surge diverter can keep the residual voltage low enough to avoid the equipment being damaged. While the definition is the same between the three standards, the testing behind it differs greatly. The AS-NZS standard uses a symbol of UP and states that the voltage protection level is defined as the residual voltage as a result of the 820 microsecond test waveform at a test current of 3 Ka. Note, however, once again, there is no test procedure. The IEC standard also uses the symbol UP. However, it defines the voltage protection level as being the residual voltage when tested at I nominal on the 820 microsecond waveform. The UL standard uses the symbol VPR, also known as the voltage protection rating. It's tested on the 820 microsecond waveform at a test current of 3 Ka, similar to the AS-NZS standard. Now we know about the different parameters of a surge diverter. Let's look at why there are so many parameters anyway. In simple terms, it comes down to the intended location of the surge diverter. No one surge diverter is designed to protect an entire facility. There are devices for shunting large amounts of energy, and there are some for allowing fine protection. So the ideal and recommended solution is to install multiple coordinated devices so that protection cascades throughout the facility. This approach ensures the solution reduces the voltage low enough to protect the equipment while having the ability to divert sufficient energy to ground. The idea of zone protection is common amongst the three standards. Whilst the information is displayed in various formats, standards all seem to agree on the three locations being described as the service entrance, distribution level, and the final subcircuit. The service entrance is the place where the main incoming power enters the facility, so generally the main switchboard. Devices for installation here are more powerful, as they are required to deal with the effects of lightning. But whilst these devices can handle a lot of energy, they still typically leave quite a high residual voltage, which may mean they're not adequate for protection of electrical appliances or electronic circuits. The distribution level refers to any distribution board or submains located downstream of a main switchboard. The devices here can still handle reasonably large surge currents. However, they have a lower residual voltage, making them suitable for protecting electrical appliances. But note that sensitive electronics may still pose a problem. And this leads to the final circuit, which is any final subcircuit or sensitive piece of equipment. The devices here are typically series connected and installed on an individual circuit basis. The AS-NZS 1768 represent this information in the form of a table and provide a description of the point within the installation and makes recommendations on how large a surge diverter should be. You'll note that the service entrance has three possible ratings, C1, C2 or C3. This defines the likelihood of receiving energy from lightning or other more severe transients. The worst case scenario is C3, and that is where the building is fitted with a lightning protection system. A lightning rod is a lightning attraction device and actually increases your likelihood of receiving a direct strike. The lightning rod itself is just there to control the impact point to allow better control of where the energy goes. What this means, however, is the surge diverter actually needs to be larger and more powerful to cater for the lightning strikes. Category C2 is a facility that does not have a lightning protection system. However, is fed from long overhead power lines, or the facility itself is large and could possibly receive a direct strike. This is where one must refer to the isochronic map and determine the likelihood of a direct strike. If the likelihood is small, a device with a lower Imax could be used. However, if the likelihood is high, then an SPD with a higher Imax should be used. In category C1 is where the facility is fed from underground service, and therefore the likelihood of damage as a result of lightning is reduced. The IEC 61643 follows the same concept, with Protection Zone 1 being the service entrance, Protection Zone 2 being the distribution zone, and Protection Zone 3 being the final subcircuit zone. Note that this standard puts more influence on the class of SPD rather than nominating a KA rating. Class 1 being a Type 1 device with an I-impulse rating and tested against the 10350 waveform, whereas Class 2 and Class 3 are both tested on the 820 microsecond waveform. Class 2 being the device for the distribution level, and Class 3 being designed for the final subcircuit. Then there's the IEEE or UL standard, where they use location categories. Location category C refers to the service entrance, B is the distribution board, and A is the final subcircuit level. This standard does provide recommended ratings for the Imax of surge diverter. The higher the Imax for category C, the lower Imax for category A. So to help us understand the correct application of surge protection, it is useful to remind ourselves of the fundamental purpose of surge protection, and that is the prevention of hazardous potential differences. Many people get caught up with industry buzz terms or simply believe that the most important feature of a surge diverter is its ability to conduct current. However, what use is this feature if the surge diverter doesn't limit the voltage to a suitable level, a level in which the installation equipment can sustain? Thereby, simply by ensuring that the voltage protection level is below the insulation capacity of the connected equipment, will ensure that the voltage is kept low enough to prevent arcs from occurring within the equipment. The next important factor is to select an SPD with a nominal current and, where relevant, an impulse current higher than the surge currents expected at the SPD's installed location. This ensures that the residual voltage remains below the quoted UP of the SPD. That brings us to the conclusion of our session, and I hope you've found it beneficial. If you have any further questions, please contact your local NHP sales representative. To find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. Thanks for joining.